Hello and welcome to the 8th lesson of the Big Data Hadoop Administrator course offered by Simplilearn. This lesson will cover the details on administration of Hadoop. Let us start with the objectives of this lesson in the next screen. After completing this lesson, you will be able to describe Namenode or Datanode directory structures and files, explain file system image and edit log, define checkpoint procedure, explain the reasons for Namenode failure and identify the steps of recovery procedure, describe the importance of safe mode, metadata, and data backup, identify the potential problems faced by Hadoop administrators and their solutions, list the steps of adding and removing nodes. Let us proceed to the first topic of this lesson in the following screen. A newly configured Namenode creates the directory structure as shown in the example given on the screen. Here, dfs.name.dir property is a list of directories where each directory contains the same content, thereby providing the flexibility even if one of the directories is an NFS mount. The NFS mount permits HDFS, that is Hadoop Distributed File System, to be mounted as a component of the client file system to ensure that data processing logic is near to the data. The version file, which is a Java properties file, contains information about the version of HDFS that is in use. Example of a typical version file is shown on the screen. Let us understand the Datanode directory structures and files in the next screen. Datanodes do not have to be formatted, as they create their storage directories automatically on startup. The key files and directories of a Datanode are shown in the example given on the screen. A Datanode's version file is similar to the Namenode's file. Example of a Datanode version file is shown on the screen. Let us learn about the file system image in the following screen. The file system metadata is stored in two different parts, the FS image and the edit log. The file system image, that is FS image, represents a point-in-time image of the file system's metadata. But this file does not get updated for every file system write operations because updating consumes more memory and also slows down the system. The FS image file in the file system contains a sequential form of all the directories and file inodes. Each inode represents a file or metadata of directory and contains file information for the directories. The FS image does not have any information about the data stored in Datanodes via blocks. In fact, Namenode is responsible for mapping in memory, which is constructed after receiving the local list from Datanodes. In case the Namenode crashes, previously created FS image can be used to get most recent stage by applying all operations from edits and transactions. The edit log contains a series of files called edit log segments, which represent all the name system modifications made since the creation date of the FS image. This is done to ensure that no operation is lost due to machine failure. Let us learn about the checkpoint procedure in the next screen. Checkpoint is a method where FS image and edit log both are compressed into a new FS image. Through this, the Namenode can load the final in-memory state directly from the FS image, which is a better operation and thereby reduces the startup time of the Namenode. The checkpoint process has the following steps. 1. The secondary requests primary for new edit files. 2. The secondary requests FS image and edits from primary via HTTP GET command. 3. The secondary performs operations from edits on each FS image and then creates a new FS image file. 4. The secondary pushes back the new FS image back to the primary using HTTP POST. 5. The primary creates the new FS image from secondary and replaces the old one, and the old edits file is replaced with the new edits file created at step 1. In the next screen, we will learn about the configuration parameters controlling the checkpoint procedure. The starting point of checkpoint procedure is controlled by two configuration parameters: dfs.namenode.checkpoint.period. It has the default value of 1 hour to ensure the next refresh between two consecutive checkpoints. And the other is dfs.namenode.checkpoint.txns, which has default value of 1 million and is the rule to define unchecked pointed transactions number to forcefully perform checkpoint process, even if the checkpoint period has not been reached. In the next screen, we will learn about the Namenode failure and recovery procedure. Namenode failure occurs when there are no recoverable backups. In such case, Hadoop does not allow automatic recovery. However, the risk of data loss due to a Namenode failure can be reduced by hardening the Namenode system and components to meet the desired level of redundancy. The steps to switch to a new Namenode are: 1. Make a copy of the data before promoting the host to Namenode. 2. Change the IP address of the target to the IP of the failed Namenode. 3. Ensure Hadoop is installed and configured identically to the original. And finally, 4. Do not format this Namenode. We will understand the concept of safe mode in the next screen. Safe mode is a read-only mode for the HDFS cluster, where no modifications are allowed to file system or blocks. In safe mode, only file system operations that access the file system metadata are sure to work. Reading a file will work only if the blocks are available on the current set of data nodes in the cluster, and file modifications will always fail. Safe mode is required to give the data nodes time to check in to the Namenode with their block lists, so the Namenode can be informed of enough block locations to run the file system effectively. HDFS can be placed in safe mode by using the command shown on the screen. In the next screen, we will learn about the metadata and data backup. Data backup is a part of routine administration process. It is important as it prevents loss of data in case of metadata damage. The process is carried out by writing a script so as to archive the secondary Namenode's previous checkpoint subdirectory to an offsite location. The reliability of the metadata copy can be checked by initiating a local Namenode daemon and verifying its readability of FS image and capability of editing files into memory. As DISTCP tool can copy files in parallel, it is used for making backups to other HDFS clusters or other Hadoop file systems, such as S3 or KFS. An entirely different storage system for backups can be employed by exporting data from HDFS. In the next screen, we will understand the potential problems that are faced by Hadoop administrators. Some of the potential problems which Hadoop administrators face in day-to-day operations are caused due to human. Humans cause most common errors in health of systems or machines. Even a simple mistake can create a disaster and lead to downtime. To avoid these errors, it is important to have proper and proactive diagnostic process in place. Misconfiguration is another problem that Hadoop administrators come across. Even now, after so much of development in Hadoop, it is considered a young technology. Let us look at the solution to this problem. You need to perform the following steps to get rid of misconfiguration. Start with basic parameters related with storage and operation. Gain thorough understanding of what needs to be achieved and where we are. Do a lot of trial runs before moving on with changes in production environment. The next problem is hardware. One would rarely hear about a problem related to memory, motherboards, and disk controllers, but hard drive is mostly the cause of most of the problems. Almost every manufacturer do specify different measures of drive, such as mean time to failure, mean time between failures. Hardware does not fail straight away, but they degrade over time and lead to different failures. HDFS is best in detecting corrupt data blocks and automatically replicate to new copies without human intervention. In the next screen, we will understand the remaining potential problems that are faced by Hadoop administrators. Remaining factors causing problems for Hadoop administrators are resource exhaustion. It is also a major factor that causes problems. As an administrator, one should measure and track task failures so as to help the user identify and correct the processes. Repetitive task failures can occupy task slots and can also take away resources from other jobs. Therefore, it should be seen as a drain on overall capacity. Next is the host identification and naming. Incorrectly configured host configuration file will lead to a situation where client will never be able to communicate with data nodes. The other problem is network partition. It is a situation where network is unable to communicate with other hosts on segment of network. This means that host X on switch 1 cannot send messages to host Y present on switch 2. Let us learn the solutions to these potential problems that are faced by Hadoop administrators in the next screen. The solution to the problems of Hadoop administrators can be explained by eSpore. The word eSpore stands for environment, stack, pattern, output, resources, and event correlation. Let us understand each of them one by one. Environment. Always audit your environment for obvious issues. Check for the history of the system. Verify what is different in the environment now and in the environment the last time the system worked. Stack. Verify dependencies. For example, MapReduce services need HDFS services for running in healthy state. All of the HDFS depend on Namenode, and this Namenode depends on host operating system. Now comes the pattern. You should look for patterns in failures. When MapReduce tasks fail, check whether they are of the same job, assigned to same task tracker, or have shared libraries. Output Hadoop conveys its afflictions to us by method of its logs. Continuously check log yield for exemptions. Finally comes the resources. All daemons need resources to operate, and as you saw earlier, resource exhaustion is far too common. Make sure local disks have enough capacity so that the machine isn't swapping, the network utilization looks normal, and the CP utilization looks normal given what the machine is currently doing. When none of these steps reveal anything interesting, look for event correlation. That is, following the series of events that led to the failure, which usually involves inter-machine, inter-process event correlation. In the next screen, we will understand the steps for adding nodes. To add nodes to an existing Hadoop installation, the following steps need to be followed. The nodes that need to be included require to upgrade the host's name in the default directory, shown on the screen, which is separated from this DNS mapping in the default directory, again shown on the screen, for allotted IP address in system likewise needs to be balanced. In the hubs to be included, add Namenode IP location to the default directory shown on the screen. Install SSH, that is the secure shell, and guarantee that SSH keys are duplicated from one hub to different hubs in group. After this, copy Hadoop establishment documents to the hubs that need to be included and upgrade the setup records shown on the screen from different hubs in bunch. The remaining steps of adding nodes to an existing Hadoop installation are given on the next screen. After performing the steps shown on previous screen, add the IP location of adding hubs to the default directory shown on the screen in the name node and append the IP location of added hubs to conf/slaves in the name nodes. After all the steps are performed, start Hadoop Prepare to include new nodes. First time, do it physically, and at later stage, Name Hub will naturally accumulate them. Next, balance the data to new added nodes by using the command shown on the screen. In the next screen, we will understand the steps for removing nodes. To remove nodes, the following steps need to be followed. 1. Add list of data nodes that need to decommission to exclude file. Assume this file is located under Hadoop/conf directory on Namenode. 2. Modify the name node hdfs-site.xml config file to set the property for dfs.hosts.exclude. You can ignore this step if you have already set this property. 3. Modify the name node mapred-site.xml config file to set the property for mapred.hosts.exclude. Ignore this step if you have already set this property. 4. Now update the name node using following command shown on the screen on name node only. Check the name node on port 50070 admin UI to verify if the data nodes in exclusion list are in decommission in progress. 6. Then start the process of replicating blocks to other data nodes in the same cluster. Once the process of all data nodes decommissioning is successful and all the blocks have been replicated, you can shut down all decommissioned nodes, that is, reboot them. 7. Remove decommissioned nodes from slaves file on all nodes and refresh the nodes on name node using the command shown on the screen. 8. To avoid the situation of unbalancing of the nodes, we need to run the balance utility after nodes have been added or removed. 9. Therefore, run Hadoop. Let us summarize what we have learned in this lesson. The file system metadata is stored as fsimage and editlog. In checkpoint procedure, both fsimage and editlog are compressed into new fsimage. The starting point of checkpoint procedure is controlled by dfs.namenode.checkpoint.period and dfs.namenode.checkpoint.txns. Name node failure occurs when there are no recoverable backups. The risk of data loss can be reduced by hardening the name node system and components to meet the desired level of redundancy. Tool used for metadata and data backup is DISTCP. Humans, misconfiguration, hardware, resource exhaustion, host identification and naming, and network partition are the common issues that Hadoop heads confront in everyday operations. eSpore provides solution to the problems of Hadoop administrators. This concludes the lesson on Hadoop administration and maintenance. The next lesson will focus on Hadoop ecosystem components.